The number of new features I've added, there's the ability to overlay data from different simulations or measurement data. I've added something called MEXTRAM 504. MEXTRAM is the device equations for a bipolar transistor. It's very popularly used in IC design, but there are a number of hi-fi audio people that use it. LTSpice did it, so basically I had to add it so that people could move from LTSpice to QSPICE. However, I implemented the self-heating for this transistor, which LTSpice didn't do. And while I was at it, I added self-heating for a resistor. And when I have enough time, I will actually add self-heating for all the standard SPICE devices, so we could have a thermal model of a whole power solution, which would be which otherwise you can't, which otherwise doesn't exist. There's solvers that will give you some libraried results on thermal, but there's nothing that'll actually solve it for you while it's solving the circuit. So that would be an entirely original new thing. There's some ability to create a schematic from a netlist. It's primitive, but it's there, and when you need it, you really need it. I'll demonstrate that in a minute. This feature, as though trivial to implement, is incredibly useful. If you point at text and press on the semicolon key, the text will turn into a comment or turn from a comment to not a comment. So you can toggle the comment status with the semicolon key, and that's really useful if you have a bunch of commands and you want to turn some on and some off. It's a very quick way of turning things on and off. It's good. QSPICE always had good PSpice compatibility for models, but at high-level simulations, people use things like repeat for and repeat syntax, where they give a piecewise linear set of data and they say repeat it so many times. And this is not used in a model. It's just a feature to PSpice, but it's useful enough that I had to implement it. The step tool is it's something that allows you to navigate a simulation that has many steps. You can look at all the parameters, different steps. You can move the cursor around. I'll demonstrate that. This is a feature I'll demonstrate also. Some simulators will allow you to put a slider on the schematic, and you move the slider around, and it will resimulate with the new value that slider is controlling. I don't like that for a couple of reasons. One is that it's hard to pick a reasonable range for a slider if you don't know what you're controlling. It can't just be 0 to 200%. So I have this little velocity-dependent algorithm that will change the number. It still needs work, but it's there. There's 2 ICs now that you'll find in the general release without NDA. And this is very important too. So the thing is that JFETs were never properly implemented in SPICE, but nobody cared because there's not very many JFETs out there, by and large, say before silicon carbide. And the JFETs that were in an integrated circuit, they tended to have a lot of production scatter, and they were only used in saturation region, not in the triode region. They weren't used like resistors. They were used like current sources to the small extent, or they're actually used as pinch resistors. Anyway, first let's for overlaying, for this bullet point, overlaying measurements with simulation data. That's an example of doing that. I'll probably demo this in real life. That's the step tool. Okay, this is the JFET I want to talk about. So these are the device equations in Berkeley SPICE. And even if you run HSPICE or Spectre or whatever, these are the device equations, and they're simply not correct. If you actually curve trace a JFET, it looks like this. And you see, okay, the saturation is okay over here. This is called saturation region of a field effect transistor, whether it's a MOSFET or JFET. This is called the triode region or linear region, and it doesn't transfer between regions correctly at all. So in QSPICE, now I've fixed that. I've added 2 parameters that will describe this. You can encapsulate the behavior of this transition from triode to saturation. And I will be able to improve the MOSFET equations with this also, because normally MOSFETs are simulated very accurately in SPICE, but power MOSFETs are not, because a power MOSFET, being a vertical device, has a very nonlinear gate drain capacitance, because the gate and drain are opposite each other, and the gate drain capacitance changes dramatically depending on whether the channel is enhanced or not. It's like you're moving the plates of a parallel plate capacitor, 5x, whether the transistor is on or off. And you don't have that behavior if you have a lateral transistor where the gate and drain are next to each other. But if they're on top of each other, if the channel is conducted or not, you have a huge change in capacitance depending whether the transistor is right or wrong. And so you don't use the fancy MOSFET equations that are available in SPICE, like BSIM or EKV or any of that, or HiSim, to model a power MOSFET. You use simpler equations, and then you do something about the charge model. So this gate drain capacitance is the Miller capacitance. You have to model that, and you need to use other methods to get that. Anyway, the saturation region of these simple equations aren't quite right either. They're not as dramatically incorrect as this, but there'll be a benefit. They'll be able to carry some of this work from the J field effect transistor to the insulated gate field effect transistor. So that'll eventually be an old thing. And what happens here is a couple of things. One is, we sell JFET, so we need to simulate them right. But the way you usually get people to move to a simulator is not by being faster or having a better user interface or being free. The way you get people to move to a new simulator ultimately is by being able to do things that no one else can compute. So they don't have a choice. And once these things move in the JFET and the MOSFET, we can say, if you want to simulate a JFET, the only way you're going to do it correctly is in QSPICE. And we won't be lying. We'll be telling the truth. And that'll be the same for MOSFETs, power MOSFETs. So that's the reason for dwelling on this topic, and that's why this is important. Okay, but getting this data was not easy, because in a data sheet, people who make JFETs have very good test setups for the electrical characteristics part of the data sheet. The things that's black and white with numbers. That's basically the contract of a data sheet. Then you have all these plots and curves in the data sheet, but those curves are basically for entertainment purposes. They're not particularly correct. So getting this data was not easy. And you have to use a pulse test. You can't have self-heating, because even in this tiny, there's a little bit of self-heating you can see in this transistor. If you look at this top curve, it's bowed down a little bit. That's physically impossible for a JFET to behave like that unless it's changing temperature. Okay, this curve should be straight or start avalanching or have deep impact ionization conductivity modes. There should be conductivity it should be curved the other way if it's not straight, but it's curved down. I'm getting some self-heating. So even though I'm doing like 100 microsecond pulses every quarter of a second, I'm still getting some self-heating that's impacting this thing. So anyway, to measure this stuff, this was the setup I used. There's a time base here. And the choice of components was that this is all through hole, because I have no way of dealing with surface mount. I just don't have any gear for soldering anything surface mount. So it's all through hole stuff. So this is the circuit I use. Okay, I have a time base, and then I have to level translate. I have to tell the DAC when to fire the convert. I have to pulse the drain, and then I have these samples and hold. I have to store it so that the successive approximation DACs will look at the stored sample, just capture at the very end of the pulse. And then this is like an electrometer. Electrometer, you take a giga-ohm resistor and you put it between the output and the inverting. It's a transimpedance amplifier with a giga-ohm resistor. You can measure, that's your electrometer. Except my electrometer can measure, tens of amps. And the reason for doing that is so I don't have to worry about 4-wire techniques in measuring I can just put alligator clips on the transistor and curve trace. I don't have to worry about careful 4-wire techniques. And This is kind of cute here. So I have to take a DC level and pulse it. So this is a fairly standard technique of using a JFET to chop a signal. But if you do this, you get some charge injection. So this doesn't look like a little square wave. It's a square wave with big jolts that it can be bigger than the wave itself. And so what I did is I put this other transistor. See, this transistor here, whether it's on or off, it's still ground, but it injects the same amount of charge into the same network, so it cancels the charge injection from that. It's kind of clever, and I haven't seen it before, but it gives me a nice clean square step wave here, and then I go through a 1, 2, 3, 4 pole Gaussian filter, so I don't have a lot of to make it easier for my electrometer, for my transimpedance amplifier, to keep this active ground at ground. So I filter it so it looks like a Gaussian pulse. Anyway, that's the circuit. And so, I've heard that these circuits are built on circuit boards. So I used mahogany when I built it. All right, and that's the curve tracer. And so first thing I talked about is overlaying waveform data, and so this is some simulator that this professor in Hanover sent me, and he wants to know whether or not his model matches the impedance curves he measured. So here I have an Excel CSV file, and I can just drag and drop it in and overlay it, which is useful. Now, there's something you should understand about overlaying waveform data. SPICE users don't overlay. They use something called dot step, which means they set up the simulation so it'll run the same simulation many times with different values of a parameter. And so that means that all the waveform data is in the same address space. And that means that the simulator, the GUI, can be perfect as far as labeling everything correctly. If you just overlay data from different simulations, there's no way that you could know that it's correct. And you look at it, you see here's V out and there's V out. Well, which is V out? It's up to the user to keep track of this data. So normally, SPICE users don't normally do overlays. They normally do dot step, because that way the waveform viewer can be perfect. And the waveform viewer should be like netlisters. They have to be perfect. If you're at a netlister, if it makes a mistake, you should say you're sorry, give back all your money, go home and do something else for a living. Netlist has got to be perfect. And so should the waveform viewer. Anyway, so it does. I've broken out of the. I've decided to enable overlaying waveform data, and it's there. All right. So I had mentioned that there is the ability to turn a netlist into a schematic, and that's useful when you have a macro model and you don't know why it runs. So here's a netlist. I type Control-C, and then I can come over to QSPICE. I hold down the Shift key while typing Control-V, and then instead of pasting that text, it pastes it as components with all the nets labeled. So this is sort of like starting a going into CirCAD and having your components before a layout. Then you would, these are all the components. It's going through the list of components. I could read these nodes and try to make them, position them better. There. But if I look at this net list, it's the same net list. And then I could rearrange these components, and I say, okay, so these are both connected to one. I rearrange, I turn this. It's a layout problem. Then you have a schematic from your net list. It may look like nonsense, but man, when you need it, you can't live without it. That's all I can tell you about that, man. So let me show the self-heating thing. So here we have a resistor and a current source. I'm going to turn the current source on T equals 0, it's 0. amps, and at 1 microsecond, it's 10 milliamps. So I'm going to start, when it's doing the dot op, when it's solving the bias point, there'll be no current through it, so it's no self-heating. And then at t equals 0, I'll start putting current through it, and I can watch the self-heating. And to implement self-heating resistor, you give it 2 more parameters that define a thermal time constant and a thermal resistance. RTH and CTH define a thermal resistance and time constant. We run the simulation, and we look at the output voltage. So I put at t equals 0, it's 0 volts, and then I go up at 0 amps, and then I put 10 milliamps. How many milliamps? I put 10 milliamps through the 1K resistor, so I have 10 volts, and then here is like a 2 millisecond thermal time constant, and the thing settles in. Okay, so that's the self-heating of a resistor. And now the little semicolon key. If I point at this attribute and press the semicolon key, it turns blue. That means it's a comment, and that gets rid of those attributes. So the semicolon key is really useful because you might have a whole bunch of analysis commands. You want to turn on the dot AC and turn off. You want to turn off the dot tran and turn on the dot AC, or vice versa. Go back and forth between those two. So the pointing at something and pressing the semicolon does that. Let's look at the step tool. So I should have closed these others. Okay, so here we have the Hello World SPICE simulation, square wave into an RC filter. But I'm going to step the amplitude, the resistance, and the capacitance. And so this is the way you normally overlay simulation results in SPICE. You do it with that step. And then, so this is all V out. It shows them in different colors, and you can, the step tool helps you navigate these things. So if you press F6, that's the step tool. And here you have the color legend. You can sort them by different parameters. Let's sort them by resistance, and let's highlight all the 1K values. Apply. So that shows you all the simulation that where the resistance was 1K. Let's sort by C, and let's look at all the 0.09 microfarad ones. That's that's a fixed capacitor, but I'm varying the amplitude and the resistance. Another thing the step tool will help you navigate the attached cursor. So here's you put attached cursor on here, and you use up down arrow keys and have it step from step to step. But if you look at the step tool, it's highlighting the one it's highlighting. It's putting the software cursor to indicate where the attached cursor is attached. Or I can click on one of these, and the attached cursor moves around. So the step tool is useful. You can navigate a simulation with a lot of steps. The alt mouse wheel thing. Let me show you what that does. Okay, so here we have again the Hello World SPICE simulation, square wave into a RC filter. But what you can adjust these values with the mouse wheel. So if I double click on this and hold down the Alt key and spin the mouse wheel, it changes and resimulates. And it's velocity dependent. So if you turn it very, very slow, it's like pico part per million steps. And if you move it fast, it'll get away from you real quick. So you may find that still needs some work. I think it's a little bit too willy-nilly, and it's a little bit too, it gets too excited. I have to settle down that behavior. And because the simulation and GUI are in different processes, it's hard to instantaneously resimulate. You have to stop doing it, and then it will resimulate. You can spin it, and then you have to wait half a second, and then it'll resimulate. Now, one other thing I wanted to point out was that these two models are available to everyone now. Right, so this is a part of the radar chipset. Right click, open example schematic. So this is a demonstrating this this part. And the cool thing about it is that the whole, everything is modeled. Here's the I squared C clock and data. So it first writes 3 bytes. The first byte programs the soft start, the second one programs the gate voltage, the third one enables it. But you can program the dead time. There's about 100 parameters. There's 63 I squared C registers, and there's 2 bit fields that controls about 100 aspects of the part, and everything is modeled in this because in QSPICE it's easy to present an infinite amount of digital logic to your SPICE simulation. So that's the. I guess I can do the. Here's a simulation with the updated MOSFET device equations. Here I overlaid them, and when I did the PowerPoint slide, had the data and the simulation in different next to each other. But here I can overlay them, and I can actually overlay the. I'm running both the new and old device equations. So that's the old. This is the old device equations, and then these are the updated QSPICE device equations.
And appreciate your